All right, lecture time. Equipment details, some more about electricity, electrodes, kind of diving in a little deeper to some of these things that we already know about. So this is chapter 3, if anyone's in the book, more about equipment setup and controls. So power source, everyone's familiar with using these different welders here, but we're going to go in a little bit more, talk about some more details. The power source, no matter what welder you're using, you have a power source, obviously. The power source is going to control these factors: the input voltage, open circuit voltage, and of course the output ratings and performance, and then what's called the duty cycle. So we're going to talk about what those things are. The input voltage would be, at least here in the US, we either have 110 volt outlets or 220 volts outlets. This is single phase, of course. So the 110 is your standard household outlet. The 220 is basically double that. Sometimes it's called 240. It's basically the same thing. And some of our welders just work on 110. Some just work on 220. And some you can switch back and forth to either one. Of course, with 220, you can weld thicker material than you can with 110. It's more juice behind it. Open circuit voltage. I was actually talking with Michael about this, I think, in our last class on Friday. So open circuit voltage is the voltage output range of the power source before an arc is established. The arc starts, of course, when the trigger is pulled. The open circuit voltage will affect how the arc will start. Now, most of the machines, a lot of the machines, I guess, you don't see the open circuit voltage and you don't have any control over it. It just is what it is, and that's fine. That's because for GMAW, the open circuit voltage matters a lot less, matters a lot more with SMAW or stick welding. So when you use any of the what's called the suitcases, the wire feeders, the V-Sense feeders in the booths, those you will see the open circuit voltage. Our power source will flash between two numbers. There's going to be a bigger number. It should be between 60 and 80. And then the smaller number, which is what you're actually setting your voltage at. So that's what you're seeing when you're using those machines. Again, not very important for MIG welding. Something you might have to know for stick welding. It might affect, which electrodes you want to use and stuff. But that is, it is what it is in those power sources. You don't change that. So output ratings and performance, pretty self-explanatory. Output is the voltage and amperage when the current is flowing, when you have the trigger pressed down. Performance would be how the machine actually welds. Duty cycle. This is something that is important to know, especially if you're going to buy your own machine. It's a good thing to look at depending on what kind of welding you're going to want to do. So the duty cycle is the percentage of time in a 10-minute period that a machine can run at a rated output without overheating. So by a rated output, that means at X amount of volts. That's the rated output. So every 10% represents 1 minute of operation. You can range with the duty cycle from 20% to 100%. That the difference there depends on the internal wiring of the machine, the other types of internal components, insulation inside the machine, and the amount of cooling that might be available, if it's a water-cooled machine, say. So to explain a little bit more, if you have a machine that has a 60% duty cycle, that means at a certain output rating, at say 20 volts, it can weld consistently for 6 minutes out of 10. Once it hits 6 minutes, it's going to overheat and you're going to have to stop and you let the machine cool down. Most of the new machines are going to have, some kind of warning that would tell you if you're hitting the duty cycle. Some of the older machines, you could actually overuse them and overheat them. It's not something we really have to be concerned about with the welding that we're doing in the shop. It's not terribly often that you hit the duty cycle. Again, you do want to know it depending on the kind of welding you're going to be doing. But it's like for me, for instance, I have those Lincoln 210 MPs, and I do, different kinds of fabrication in my shop, but it's not like big, long, huge, heavy duty welds on a lot of them. So I've hit the duty cycle on my machine a couple of times, but that was more when it's also when it's really hot outside and just like everything in the machine is already pretty warm. And then my machine, has that computer screen. It pops up with it stops welding. It pops up with a little like thermometer symbol, and you just got to let it sit and let it cool. Sometimes I might get out an air hose and sort of blow some air into the inside of the machine, because that can help cool it down. But you just wait and wait till it's ready, and then you can use it again. It's not a big deal, but obviously a higher duty cycle just means like heavier duty, better components inside the machine. There's different classes, 1, 2, and 3. Class 3 would be the lowest duty cycle, and that's home or hobby use. I actually can't remember what exactly the Lincoln's duty cycle is, so maybe we'll look at that in next class if you remind me. They should all machines should have like a little something on the back side or maybe underneath when you're looking at the electrode wire in there or something, but it should have something on the machine that tells you what the duty cycle is. More about electrical terms and concepts. There's something that you might encounter called inductance. So this is the property in an electrical circuit that slows down the rate of current rise. Okay, that's the actual technical definition. How it affects welding, it means that it affects the way that the molten metal drops separate from the electrode as the current squeezes the electrode. So this is all happening within 1 millisecond. But basically what's happening is, you press the arc, the metal, the electrode feeds down, and it short circuits to the base metal. And then inductance is what is the pinch force that pinches the wire and actually creates the molten droplet. And then the arc reignites, and then another droplet's formed, and it goes back and continues doing this. And then this is all within milliseconds. So the inductance does affect how the metal, the electrode melts into your weld. So if you have inductance control, it's going to be located somewhere on the main panel. Most of our machines don't have inductance control. The Lincoln does, and I think that's the only one if I'm remembering right now. So if you remind me, and hopefully I'll remember, I'll show you that on the Lincoln, how you can control that. So for GMAW, you use it in short circuit transfer. It doesn't really affect how the electrode melts as much for flux core. And a basic rule is as the electrode diameter increases, the amount of short circuit current that you need is going to increase. Therefore, the ideal amount of inductance increases. So if you do have those settings, something you want to keep in mind is thicker wire means higher inductance. In short circuit mode, maximum inductance, a high inductance all the way up, means that the current rises slower. And this means you have more penetration and a more fluid weld pool and a nice flatter, smoother bead. So I remember some of you in class on Friday were having some trouble with having a really like peaked weld bead. If you were on a welder that had inductance control, you might want to turn that inductance up if you're having that issue, and it's going to flatten out that weld pool. We don't have that available on all of our machines, so if you don't have it, you don't have it. A low inductance, the lowest down you could go, means that the current is going to rise faster. So when you click that trigger, it's going to go fast all the way up to whatever the current is that you've set it at. This means a more convex, so more peaked bead, a more kind of bulged up bead, also does increase the amount of spatter. So most cases that's less desirable. And you have a colder arc. Maybe you would want a colder arc if you're doing some nice thin sheet metal, make sure you don't get burned through and stuff. And so you would turn the inductance down. Arc voltage and slope. These are just terms that you might hear, around in the welding world. So I want you to be familiar with these, even if we don't always, we aren't using these or encountering these every single moment that you weld. So the arc voltage, that's the voltage output when the arc is present, when you have that trigger pressed down. And then you'll hear something called slope, which is the slant of the volt amp curve. Now I'll have a picture in the next slide to illustrate that, but I want to explain a little bit. So this illustrates, it tells you about the operating characteristics of the power source under an electrical load. That means when the electricity is flowing, when that trigger is depressed. It kind of tells you a little bit about what is going to be happening in your weld, how the weld is going to look at the end of the day. So the slope here is automatically set in mini machines. We don't have, again, as far as I can remember, I don't think even the Lincoln gives you control of the slope. So it's mainly on most of these machines that you have in the shop, you don't ever encounter this. If you've done any TIG welding at the shop, I believe our TIG welders do have slope control. It's probably something that you didn't get into even in the intro TIG class, but with TIG welding, it is something that you usually have a little bit more control over because it's more necessary to have control over it. For flux core, something to know about the slope is that flux core operates best in the flat mode. So now, what does this look like? Hopefully this picture kind of illustrates actually what I'm talking about, what the slope actually is. So this is a constant current power source. This is the power source for stick welding and for TIG welding, right? Constant current, that means the amperage stays the same. So when you're here at the operating point, you have the amperage, the sort of band of fluctuation of the amperage is very small. The fluctuation in this picture is like from this dashed line to this dashed line. So a very small fluctuation. Remember, even in a constant current power sources, nothing is actually constant. It's just relatively constant relative to the voltage. So we call it constant. So the amperage can fluctuate just a little bit within that band, and then the voltage in a constant current power source fluctuates a lot more. It could be anywhere in between this line and this line. And there you have your operating point. So you would set the amperage right here, and then the voltage would fluctuate accordingly, according to how far you are, how close you are, and stuff like that. Now, this is our constant voltage power source. This is the power sources that we use for GMAW and for FCAW. So this is a much flatter slope. It's not this big arcing curve. And here you see the fluctuation difference of the voltage is much smaller, again, between these two dashed lines. And then the fluctuation of the amperage is quite a lot larger. It can fluctuate a lot more anywhere in this operating point. So maybe that will help you to sort of visualize in your head what the slope actually means. And if you have a machine ever that you start to be able to control it, at least you have something to start from mentally as to what that actually means. So some additional equipment that you may encounter out there for welding: pulsers and auxiliary pulsers. Some machines already have a pulsing system. Remember, one of the standard deposition modes is a pulsed spray transfer. But you can only do that with a specialized power source that actually does that pulsing. You can also buy an auxiliary pulser and plug that in, add it on basically to an existing machine. And that way you can manually set the desired pulse time, so you can set how long it stays high and how long it stays low. It's something, again, that's more often used in TIG welding than for GMAW, but sometimes you might need to use it. And for any of the newer transfer modes, you have to have a specialized power source like that. Now, the V-Sense feeder, we have V-Sense feeders. They're often referred to as suitcase welders. Kind of look like a little suitcase, you carry them around. Those are the ones that are mounted up on the wall in the welding booths on the left side when you walk in, and you have to plug them into your power source down below, and then the wire is way up there. So we've kind of talked through those. I think everyone has probably gotten to use those once, hopefully. And they are a little bit different than our regular welders, that everything is contained within one welder, the power source and wire feeder, and etc. So the V-Sense feeder, if you're using it with a constant voltage power source, that's the power source we use for MIG welding. With a constant voltage power source, you just basically set it up as an external wire feeder. You can also buy just external wire feeders. You can basically plug them in, and they're just a place to put a bigger to put more wire or whatever. So it basically works as an external wire feeder in this case when if you have just a constant voltage power source. So our shop power sources, those little blue boxes down below, those can be set to constant current or constant voltage. And if you have an internal switch in the feeder, that you would switch it from constant current to constant voltage for the V-Sense feeder itself. But the power source can be either one. So in this case, you kind of don't have to worry about it quite as much, I guess. So the idea was when you have a constant current power source, you have that extra clip up there that senses the voltage and feeds the electrode at the proper rate for that voltage. That's why it's called a V-Sense feeder. So the reason for that these exist is because constant current power sources are the ones used for stick and TIG welding, right? So the idea is that if you have, on a job site somewhere, you already have a constant current only power source because you're doing a lot of stick welding, then you can buy a V-Sense feeder, you can plug it into the constant current, and you can still do MIG welding, which requires constant voltage, right? So it allows you to use a constant current power source to do constant voltage, which is a benefit. If you already have a constant current power source, you don't have to buy another one, you just buy a V-Sense feeder, right? Our shop ones can be either one, so we could use a V-Sense feeder, we could use an external wire feeder, we don't have to have a V-Sense feeder, we could do whatever we want. But we do have V-Sense feeders, so that's a little bit, hopefully some more explanation of what those are. And remember, when you do use those and set them up, our power sources have to be set all the way to V-Sense feeder, all the way to the right. There's a setting for MIG welder, but that's not the one we want because we're using a V-Sense feeder, which can be used for constant current or constant voltage. We have to tell the power source that's what we're using. Hopefully that makes sense. If you have any questions, then you can ask me in class when we're in front of one of those machines. So now a little bit more about wire feeders. This power source I wanted to show you. So this is a wire feeder setup up here where the wire is contained inside here. It's different than a V-Sense feeder, but it still is a separate wire feeder and power supply. So the wire feeder, everyone's looked, inside their welders and is familiar with this by now. You have some kind of drive rolls, you have a guide here, you set the tension here. It's going to look something like this. You do have to make sure when you're welding on your own that the grooves in the rollers are the right size for your wire. Also, you want to make sure that you don't over tighten this tension. I have mentioned that. Having a little bit of a looser tension is actually better because it prevents bird nesting, which is when the wire is trying to feed forward, but it's encountering some kind of blockage probably up at your gun. And if it's looser, then these drive rollers can just kind of slip. And if it's too tight, then they can't slip and they keep feeding forward and they back up right here and it's real annoying. So having a little looser tension is actually better. So the grooves here, there can be different kinds of drive rollers. There's ones like these that have multiple different grooves in them, different sizes of grooves. Though most of the ones that we have, if I'm remembering right, you have a totally different drive roller. So you would take one out and put a different one in if you change the size of your electrode wire. So again, this isn't something that you encounter a whole lot in our shop, but you obviously do need to know about it for your own welding. So just make sure that if you're welding on your own, you do have the right size grooves for the wire you're using. And they all should be stamped on the outside. It should be pretty clear which one is which. You can also have different shapes for the grooves. They can be knurled, like this one here, a V groove or a softer U groove. V groove could be used, is better for hard wires. U grooved is for softer wires. All of ours are U grooved. This is just kind of a standard range. But sometimes if you have this harder casing electrode, you need to have a V groove. A knurled is sometimes better for having a little more grab on that wire and pushing it a little bit more. But generally, a welder is going to come with its own drive rollers, right? Then you should have a couple different size options that come with it. So this is everything that we use in our shop is a push type wire feeding system. It pushes the wire through with the drive rollers all the way through out to the end of your gun. Some other options are spool guns or push-pull systems. So a spool gun has a little motor in here, and you put the electrode right up here instead of way down in your machine. So it feeds directly from this wire and just straight through out to the end of the gun. And this is usually used for soft wire like aluminum or bronze because it has, a super short distance to travel there. You see it just pushes straight through, doesn't have to push through a flexible hose, which is much harder for a soft wire like aluminum. The push-pull systems are the newer, fancy, high-tech, where they have the spool down below in the welder like normal, and you push it through the drive rollers there. But it has an extra system up here with extra drive rollers that also pull the wire from right here up top in the gun. And so it gives it, again, that shorter distance to travel, and it gives it, it's much less prone to like getting stuck if the wire is, or if the gun is bent or something. It does make a much bigger and bulkier gun. The spool gun is also a bigger and bulkier one, and you can use less wire at a time, so you have to switch it out more often, which could be time consuming. We do have a push-pull, we actually have a couple push-pull aluminum welders. And my goal is to get that set up so we can try it out soon, hopefully. So those are fun. And you just can, weld aluminum. Super easy. It's awesome. A little bit of maintenance tips. You definitely want to keep your wire feeder dry. You keep your whole welder dry. Water's not good for electrical stuff. If you have any electrical malfunctions, maybe look into it yourself, but obviously it's better practice to have someone who's an electrician and knows a little bit more about electricity look into it, make sure you don't hurt yourself or mess up the machine. Make sure to use authorized parts in the circuit boards. Replace the rollers if they get worn. Look at the guides and stuff. When you're switching out wire, you might, blow it out with compressed air, clean it out a little bit. You don't want it to become super clogged with like particles if you're in a shop where you're doing also a lot of grinding. So just kind of like general obvious things, keep it clean, keep it free of a lot of dirt and dust and stuff like that. Now, the electrode wire itself, a little bit more about that. This is in chapter 5 if anyone wants to check that out in their book. A little bit about the manufacture. It starts from a large coil of heavy wire, and then it's pulled through smaller and smaller dies to get it to the desired size. Then it's annealed, which is a heating and softening process, basically. You don't want the metal to be brittle, of course, because it's going to snap and break. Some of the materials, like stainless steel, have to be annealed several times. If they're different alloys and stuff. So this is all controlled and done, in places where they know what they're doing. Now, for flux core electrodes, those are a little bit different. They start with a U shape, and then it's drawn, and then it's filled with flux, and then kind of drawn through different dies to close it into a solid wire, and it's sized to the final diameter. And this is what it looks like blown up. There's actually flux inside here. So the flux, just like with stick welding, has deoxidizers, you have slag formers, arc stabilizers, whatever you need for that particular electrode, for the kind of welding you're going to be doing with it. Then the flux is sealed into there, and then we went through all of that. So the classifications, this is the stuff that is kind of a pain in the ass and gets a little bit more complex, at least for me. I'm going to go over, some of the basic stuff here. So hopefully you can recognize different electrodes when you see them out in the world. But we don't have to memorize every single thing and what every single thing means. And we've talked a little bit about these for GMA electrodes for carbon steel. So we should all be pretty familiar with what these look like. E for electrode, R for rod, the XX designates the tensile strength, S is for solid wire, and then you have the X tells you about the specific alloy, deoxidizers, and whatever that are in that electrode. Now, for flux core, it looks a little bit different. You have E for electrode. You don't have an R here because it's not a rod. It's not solid. It's a tube. Then you do have two X's again, but the first X is the tensile strength. The second X is not the tensile strength. This is the welding position, either 0 or 1, flat and horizontal, or all positions. Then T indicates a flux cord. T is for tubular. And then the X tells you about the usability and performance capabilities, some of those specifics. So basically the way I think of it is ER, you know, that's a GMA electrode. E with a T there, you know, that is a tubular electrode for flux core. And it's good to remember that that extra X does tell you about the positions, not the tensile strength. So just like quick ways to sort of recognize what these are, even if you don't remember what every single number means and every single thing means. Now, this is for low alloy steel, meaning it's not just carbon steel anymore. It's in a different family of alloy steel, but the lower alloy steel, where there's not as many extra added components into the steel, this is what that electrode designation looks like. So again, EXXT is the same. We have an extra X here, and then of course this X here. So E for electrode, T for tubular. Again, that's easy to recognize. If it has an extra X after the T, then you know it's for low alloy steel. That's, again, the way I think of it. So this is tensile strength here. This is welding position again. T is for tubular, flux core. Then this X tells you the usability and performance capabilities. And this X tells you the chemical composition of the deposited weld metal. So you don't have to memorize, you know, what each thing like this is going to mean or what it looks like, but just like we want you to recognize this is flux core for carbon steel, 2 X's, E and T. This is flux core for low alloy steel, E and T, 2 X's, and extra X after the T. All right, now for chromium and chromium steel. This one is a little bit different. You'll have the E and the T, T for tubular, flux core. You have 3 X's in the middle though, okay? So that's the difference. This is its classification according to its composition. T for tubular, and then this extra X on the end, this tells you the shielding medium. So remember that some flux core you can use gas with flux core, so it's gas shielded and flux core shielded. We talk a little bit more about those designations later, but this extra one will tell you a little bit about that. See, 3 is for none; you don't have to have gas, and then these other numbers are for different gases. So again, the recognition that if there's 3 X's in the middle, that's for chromium or chromium steel. 2 X's with an extra X, low alloy steel. 2 X's only with an E and a T, that's for carbon steel. And of course the X's stand for actual letters and numbers. You know, it's not going to be an actual X, right? It's just a stand-in. Electrode material itself, you usually get it in, you're going to get it in spools, 4, 8, or 12-inch diameter spools. Some of them have just like a wooden form. You have sometimes a metal wire form, or you have these plastic ones that we have in our shop. You can also get drum packaging, these big ones where you pull out this is all filled with electrode and it feeds out from the top. This is for those extended use in like robotic applications where you're just blasting through a bunch of welds. Keeping your electrodes from contamination. This is also important. Less important for stuff like carbon steel and in a shop that's only doing carbon steel. But when you get into some of those different alloys or like higher use stuff, especially stainless steel electrodes and aluminum electrodes, this is a lot more important. So you want to keep it packaged for as long as possible. You don't need to have it open and sitting out collecting dust and stuff. Cover the wire when it's not in use. Of course, all of ours are already covered. Some wire feeders have the spool just kind of sitting up on top of the machine. So you'd cover it with something, you know, whatever you have around. Make up a little metal box you put over it. You don't want to, you know, handle it a lot. You want to try not to have your super dirty, gross stick gloves that you're getting all your, you know, gummy hands on it. Work in a clean, dry area, obviously dry. You don't want water anywhere around or any kind of moisture. If they're going to be idle for a long period, then you want to take the spools off because the carbon steels, even though they have a very thin copper protective coating on them, they can start rusting eventually, especially if there's like moisture in the air and stuff, and then they get all kind of rusted up on there, and then that's going to be bad. So you want to take it off and cover it and put it away nicely. Again, you know, inspect stuff when you're changing the spool, blow out any metal particles and stuff like that. Keep it tidy. So how different reasons why you would pick different electrodes. You're thinking about the base metal. You know, if you're welding a low alloy steel, then you have to get a low alloy electrode. The mechanical properties, what, you know, how strong it is, what it's going to be used for, service, the type of shielding gas you're using, the type of weld joint you're going to be using, because again, some of those electrodes work for only different positions, so you have to care about that. The type of weld joint, you know, if it's T-joint, lap joint, butt joint, etc. Now we're going to get into shielding gas and regulators, a little bit more about that. Chapter 4, if you've got it. And we've talked a little bit about this. I wanted to try to get into it a little deeper and hopefully explain it a little bit more. So a regulator, the purpose of a regulator is to regulate the pressure. It reduces the pressure from the cylinder to a usable level, a desired level. You know, the pressure in the cylinder is, you know, much too high to be in any kind of use for welding, so it reduces the pressure. Now, if you have a flow meter type regulator, one that looks like this, that is actually going to regulate the flow of the welding gas to the welding gun. Some of these regulators, usually the ones that look like this, these are just going to be measuring PSI, the pressure of the gas. We'll talk more about that. Some of these, you just have to look at the dials if you have a dial, and it'll designate, usually there's red and black numbers, and it'll designate if that's the CFH or the PSI or what it is that it's measuring. You just have to look at it. So the actual flow, when you have a flow meter, is much more precise. This is much more of a necessity, again, with TIG welding, the picky welding, with GMA, like, you know, doesn't care about a lot of this stuff. But it is nice to have a flow meter. For a flow meter, also, it can measure different types of gas. It'll be marked on here. So you'll have like one band that'll be for pure argon, one's for C25, one's for, you know, a different mix. So you have to look at that when you're looking at that ball in the middle and determining what the actual flow is. So flow versus pressure. The correct flow depends mostly on the nozzle size. You know, how big or how small you have it. It's just as a general, 20 to 25 to 30 CFH. In the shop, you can have it even lower, really, because it's a nice, like, stable environment. There's not a lot of breezes or stuff like that. And then, of course, adjust as necessary. It's not really something that you have to adjust a whole lot for GMA. Now, too much gas, I have mentioned this before, too much gas creates turbulence. So there actually can be too much gas, just as there can be too little gas. That was a question in the midterm, as I've talked about that before. And now pressure, that's flow. Pressure is measured in PSI, which is pounds per square inch. Now, there's not a way to convert from PSI to CFH. So if your regulator only measures PSI, then that's what you're looking at. That's what you've got. The flow is determined by the size of the orifice that's in the regulator. It's like a little hole where the gas passes through, actually into your welder. So different manufacturer will have a slightly different sized orifice, and that determines kind of what the set flow is. And you decide how much pressure is going to be pushing through there. I would generally say start at 15 to 20, adjust if you need. Again, not super picky with GMA. You don't want to go too high, though. So what does shielding gas do? It shields the electrode and the molten metal from the atmosphere, as we know. It does also help transfer heat from the electrode to the base metal. It helps to stabilize the arc pattern. It can help to control the bead contour, the amount of penetration. It does help the metal to transfer from the electrode to the base metal, and meaning that it can determine which transfer method can be used. I've mentioned that we can only do spray transfer with a higher argon content gas. So again, that's one of the things that I'm planning to get to. I just got to set up one of the welders when I get time. And then you guys will be able to try that out, which is fun. The shielding gas also assists in cleaning action and provides, it's called wetting action. That's how the like wetness of the liquidness of the weld pool. So it is important. Different gases, will do different things better. We use almost all C25. Like I said, we have some pure argon that we swap in sometimes, so I can give you a demonstration of spray transfer and stuff, but basically use C25. We'll talk more about that. So now this is talking about the flux core processes. There's flux core S, which is the self-shielded. That's the one that doesn't use gas. S is for self-shielded, no gas. The electrode itself has all the necessary ingredients. It creates its own shielding gas, has the slag there. It's great for use outdoors, just like stick welding, because the gas can't get blown around by wind. Obviously, it produces slag and then like a lot more smoke than GMAW. It is also a little bit less portable and requires more equipment than SMAW, than stick welding. But like GMAW, it has a higher deposition rate, meaning you can put more weld metal down faster. So that would be the benefit of having a flux core. And of course, this flexibility of different electrodes and stuff. Now, flux core gas shielded or dual shield process is FCAW-G. Generally, you use carbon dioxide alone or with argon, just like the C25, which is what we use. It's additional protection. Again, good deposition rate, goes fast. You have a little bit better visibility with this because you're not creating quite as much smoke as you are with the self-shielded process. All positions, some of the electrodes with the self-shielded process are only certain positions. It still produces slag, still more smoke, still less portable than stick welding. So, different things you have to consider. So GMAW you can use, these are commonly used as shielding gases: argon, helium, carbon dioxide, oxygen, or a mixture. We'll talk about the mixes that we use in a little bit. FCAW, carbon dioxide, or argon are your two main gases, alone or mixed. So argon is an inert gas. It's not super expensive, used for GMAW for non-ferrous metals like aluminum and bronze. Used with carbon dioxide for flux core, narrow bead width, deep penetration, reduces spatter. So there's good things about argon. CO2, this is a reactive gas. This is why we don't call MIG welding anymore. MIG stood for metal inert gas. Now we call it gas metal arc welding because we can use reactive gases like CO2 with it. We've figured out better ways to weld. Yeah, if you use it alone, it's more spatter, harsher arc, blah, blah, blah. So this is what we use here, a 75% argon, 25% carbon dioxide mix, C25. That is carbon dioxide 25%. That's why it's called C25. 75-25, sometimes we'll hear it called. These are some other different mixes. We just don't need to memorize all of those. I just want you to know that there are other mixes out there. For the gas-shielded flux core, you have to make sure you use the correct gas for the electrode that you're using. If you are selecting the gas mixture, you think about, what modes of metal transfer you need to use, type and thickness, joint design, all the same things, basically, and you might need to pick one or the other, some kind of different mixture of gas if you have certain different things that you're considering in your weld. Again, usually, if you walk into a welding supply store and you say, hey, I need some welding gas, they're going to give you a cylinder of C25. So that's the main thing that you're going to encounter. Gas can come in cylinders and flasks. There's different sizes here. These are Dewar flasks for high pressure gas or when a large volume of gas is required. These are some different sizes, and they have different letter designations. There's different pressures in them, etc., etc. Now, a little bit of safety note about storage. You want it to be outside, not in a small contained area, obviously upright with this cap in place. You want to have it always secured somehow with chains, not straps. The idea being that, straps can get cut accidentally or could burn or something like that, and then it could fall over. So chains are what you're supposed to use. Make sure you can still see what the mixture is on a label, that's not peeled off or, somehow obscured. Follow any safety precautions for that gas. The issue with inert gases, like argon, is that you can't see, smell, or taste them. They're not like propane or something where they have a smell, or like argon where it has a smell. So that's sort of the danger of those inert gases. A way to test for leaks is using something like you can have a test solution like this. You can also use just like soapy water, or Windex also works. You spray it on wherever the gas system part, and then it's going to produce bubbles wherever the gas is leaking out. So that's a good way, an easy way to test for leaks. You can also use a pressure gauge and test the actual outlet pressure and stuff, but that's a lot less used. So I've talked a little bit about the markings on cylinders, or maybe that was in another class, but there are markings on your cylinders. We can take a look at them when we're in class next. There's a lot of different numbers and letters on here, but there's going to be a date is the most important thing you got to find. And then that date tells you when it was either made or when it was last checked. And it's good for 5 years after that date standard. If it has a star like this, it's good for 10 years after that date. If you have an out-of-date cylinder, usually you can still take it back into your welding supply store and tell them it's out of date, and you pay a little extra fee to, for them to send it back and get it retested. But whenever you go into a welding supply store, you're not getting your gas cylinder refilled. They swap out. So you buy, sort of like the idea of a cylinder, and you have a certain size, and then you take it in when it's empty, and they give you a new full one of the same size. So you don't actually keep the same cylinder every time. But if you have one that's too old, yeah, they sort of take it back, retest it, and put it back in rotation pretty much. Here's a nice couple of lists of recommended shielding gases. This is for short circuit transfer, what we're doing here in the shop for different steels here. For spray transfer with different steels, you've got different advantages, why you would use different mixtures and stuff. So I just think these are some nice charts for you to be able to refer to if you need to. And that is it, thankfully. And if you have any questions, of course, always email me, send me a message, and I will see you in class on Friday. Have a good week. Bye.